Welcome viewers. In this video we are going to look design of substation gantry foundation in Eurocode stage 3 out of 7 stability check. So earlier to this stage 3 video we have seen already two stages of design of a substation gantry foundation in Eurocode. So here is the detail about the design stages which we have seen already and which is in future video list. So in the first stage overview of calculation which is explaining about the entire design stages, how the calculation to be presented. In the second stage we had seen the foundation and soil parameter, loads and load combinations. In the third we will be going to see now in this stage about the stability check. In the fourth, the upcoming, we will be looking anchor bolt design. In the fifth, the design of a bottom slab. Sixth is a punching and one-way shear. Seventh is the design of pedestal. Now we will look into that detailed calculation. On the screen you can see two split screen. One is left hand side the Excel calculation which is demonstrating the foundation design calculation. In the right hand side you can see the PDF file of EN 1997 part 1. So from this PDF file we need to extract the partial resistance factor in order to check the stability of foundation. So for that we need to refer table A5. So page number is 133. So here you can see the table A5 which is stating the partial resistance factors gamma R for spread foundations. So there are three set of load cases is given. So in the second set R2 is mean for SLS load combinations. So for bearing it is 1.4 and for sliding you can consider this same factor for overturning also. So it is 1.1. So here is the factors we had considered in the Excel calculation, and for ULS load combination we can consider 1 because already this ULS load combination is having the load factors, so we no need to consider a separate increased load factors. So instead of we can have it as 1 because here you can see that load combination for ULS case we already multiplied all the primary loads with 1.35 and 1.5. So no need to consider that any of the load factors. So simply we can consider as 1. So first we will look into that bearing pressure for serviceability limit state load combinations. So under this again there is a subdivision, conductor without deviation and conductor with deviation. So this Hx is a longitudinal horizontal force and Hy is a transverse force, Mo is a moment about y, mx is a movement about x direction, and z is a vertical force from the structure, and p is the total vertical forces which including the overburden soil, sulfate of the concrete foundation plus the vertical downward load from the structure. And this moment at base is nothing but the m of y plus horizontal forces which is appear in the top of the pedestal or very bottom of the structure multiplied with the top to bottom of the foundation, that is a lever arm distance which we had calculated here y bar. So this distance we need to multiply because that every structural force used to act at the top of the pedestal, it means the force will be act at here, but this horizontal force we need to convert as a moment which is at the depth of this level. So it means the top to bottom there will be a bending moment occur due to the horizontal force at the top. So this bending moment we need to consider. So that is why we are adding this bending moment which is caused due to the horizontal force also with the structural bending moment. So My plus horizontal force x into the total distance of the foundation from top to bottom. So similar like for x direction also we need to consider the hy into the vertical distance of the foundation. Next, coming to the eccentricity, actual eccentricity. Actual eccentricity is nothing but moment divided by total vertical force. So in that also we need to consider both the direction. So eccentricity Ey equal to Moy divided by the P. Similar like for eccentricity Ex equal to Mox divided by vertical force P. So next, coming to the contact length calculation. What is a contact length? It means due to this eccentricity effect, suppose if the eccentricity is greater than the limited eccentricity which we had seen here in the stage 2. So like here you can see that limiting eccentricity is nothing but the L by 6 or B by 6 with respect to the length or width of the foundation. So we already calculated this in our second stage. So if the actual eccentricity along x or y exceed this, then we need to consider, we need to find out the contact length for that. Why it is? Because when the foundation is resting over the soil, due to its external force, if it is subject to eccentricity effect, then the contact length instead of full length, there will be a reduction of length due to the actual eccentricity which is exceeding the limiting eccentricity 1 by 6th of the span. So in that case, the instead of the entire length, we must consider only the partial length which is subject to the reduction of, so this way. So then the foundation will reduce a little bit in order to support the contact to the soil. So that we need to consider here. So original foundation length is this blue color, and now it is reduced to little bit due to the actual eccentricity which is exceeding 1 by 6th of the size of the foundation. So then there will be a reduction of a foundation length during the contact with the soil. So this dispersion of length only we need to consider while calculating the bearing pressure. For this calculation, it is Ey is coming 0.97, which is exceeding the limited value along x 0.83 meter. So that's why there is a contact length value here. But in case of breadth direction, it is 0.08 for this case number 11. So if you look along y, b by 6, that is we have considered here 3 meter. 3 meter by 6 is a 0.5 meter, which is greater than the actual eccentricity. So there is no reduction in contact length, or there is no change in the contact length. So let me look how the calculation had done. So you can see here in the formula it is 3 into, so here it is defined in case this actual eccentricity is greater than the limited eccentricity which is described in the tab foundation and soil parameter I89. So here I89 means this one. So it means if you can note this case, if the case Ey is greater than the 0.83 which is calculated already, limited eccentricity L by 6, then we need to use this formula to calculate the contact length. This formula is nothing but I am writing here 3 into 0.5 into L minus Ey. So this is a simple formula. For example, we can arrive here. So 3 into 0.5 into, so we know that our length is 5 meter. We already assumed that length. So you can see here this is a length we had assumed already. So that minus, so we already calculated the eccentricity here, and close the bracket entering. So this eccentricity we need to consider. So now you can see the length, contact length is 4.59. So this is a simple way of calculating the contact length. So again, this formula is applicable only if the actual eccentricity is greater than the limited eccentricity, which means the span divided by 6. So this case to be satisfied. So then the contact length is applicable. Now next, coming to the base pressure. So the base pressure, if you see, it is somewhat difficult to calculate for this gantry foundation. So first let we understand how this base pressure is arrived. So there are simple cases. One is if the actual eccentricity is less than the limiting eccentricity, then we need to consider these all three equations. These three equations are mainly arrived by the bending equation. The bending equation, I think, the it is a basic equation everyone knows, like it is like P by A M divided by Z. So this is a basic bending equation. While we are arriving the two-way bending equation, then it should be expand to like M of Y, M of Z of Y plus M of X. If it is a two-way bending moment, then the equation to be expanded like this. So the same kind of approach we have applied these three formulas. So here you can see the P by A, which is matching to this formula, and here we are applying 6 MOY divided by L square into B. Why it is? Because so this equation we can write it in a different way also. So we know that how to calculate the stress from the bending moment. So we know that M divided by I into Y. So this is a equation to calculate the, to convert the bending moment into stress, bending stress. So you can also write this instead of Fy. Fy is nothing but it is a stress value divided by Z. Z is a section property of the member. So that section modulus of the member. So this way we can write, right, the stress value. So here that Fy is a stress, bending stress. So converting that to the soil parameter or the foundation parameter, that Fy means it is a bearing stress. So this M by Z, so we know that Z for a rectangular value, that section modulus formula for rectangular is BDQ by 12. We all already know this, right? So BDQ by 12 is a Z value. So here, sorry, it is BD square. BDQ by 12 is a I value. So we know that Y equal to, Y is a lever arm distance, Y equal to D by 2. So Z is nothing but I is a moment of inertia divided by Y is a lever arm distance. So by applying this equation, we will be getting Z equal to BD square by 6, right? because this BD cube divided by, so Z is nothing but BD cube divided by 12 divided by y equal to d by 2. So if you are equating this, then we will be getting this equation. It means b d cube. So already in the denominator we are having d, so that 1d should be cancelled. So then it is bd square, and this 12 to be divided by with the 2 and getting 6. So this is a equation for section modulus bd square by 6. So we already know that bending stress or bearing pressure we need to calculate from moment is m divided by z. So m divided by z means, so we know that z is a 6 bd square by 6. So the when we are dividing this Fy equal to moment we already having divided by z equal to, we know that bd square by 6. So we are applying bd square. So this is 6, again it is going down, so it should come up to here. We can multiply the 6 with here. So now you can see that bending stress equation is arrived like Fy equal to 6 into m by bd square. So this same approach we are applying here. B is nothing but width of the foundation, and D is L, the length of the foundation, because the bending moment is acting along the length, so that this is the main lever arm distance, the depth direction. So we are considering this L as a square and B as a multiplication factor for the, in order to calculate the stress value due to the bending moment MOY. So this is a equation to calculate the stress, bending stress, and the same approach we done for these two bending moment. So 6 My, we already have the My value here in the table, which is calculated by adding the structural moment with the horizontal force multiplied with the vertical top to bottom of the foundation depth. So 6 into MOY divided by L square, we already derived here as a 5 meter the length, and B is a 3 meter. So we already assumed this value in the stage 2 of this video. So now 6 into My is a, we can consider this as a M2. So M1 is P by A, it is nothing but the direct stresses, and this is bending moment stress caused by bending moment MOI and stress caused by MOX. So all these three are applicable only if the actual eccentricity is less than the limiting eccentricity. Now coming to the next column, so this is a summation of all the three. If the actual eccentricity is greater than the limited eccentricity, so this is a formula we already seen in our overview. That is a first stage about explaining the bearing pressure. We need to calculate this 2p into Lx. We know Lx is nothing but, we already calculated the contact length here. So this is a simple equation like 2b divided by Lx into b, in case the actual eccentricity is greater than the limiting eccentricity. But here the same formula we are applying here, but it is stating some value error. So it means there is no contact length or no actual eccentricity is exceeding the limiting eccentricity in x direction, that means the width direction. So here we know that it is 0.08 as actual eccentricity, but as per the limiting eccentricity it is 0.5. So here the limiting eccentricity is greater than the actual eccentricity. So in that case there is this way of bending moment calculation is not applicable. Sorry, bearing stress calculation is not applicable. So here the value is coming like this. And the next one is we need to combine whatever the applicable bearing pressure. So we know that if only Ey, that is eccentricity about L direction, that is larger direction, is greater than the limiting eccentricity about the same direction, then we need to add these two which are applicable. Like other direction there is actual eccentricity is limited within the limiting eccentricity, so we can consider this M3 about the width direction of the foundation, and then on the other hand in the x direction, that is width length direction, the actual eccentricity is greater than the limited eccentricity. So here you can see 0.97 is greater than the calculated limiting eccentricity 0.83. So then we need to consider the second way of calculation, that is 2b. So this one we need to consider 2p divided by lxb. So next one is only ex is greater than e limit value. So this case is not applicable for this case, because you can see this ex. So this case 0.08, which is less than the limiting eccentricity here 0.05. So this width direction movement is not applicable. So here it is showing the value error. Now if both the cases, both the actual eccentricity is greater than the limiting eccentricity, so we need to add all the three, all this PA by A direct stress with the eccentricity, actual eccentricity greater than the limiting eccentricity case of bending stresses. So this also not applicable, because our only one direction eccentricity, actual eccentricity is exceeding the limiting eccentricity. So this also not applicable. So it is showing the value error. So now we are adding all the applicable cases by applying these if conditions. So it is a big formula. Then the total bearing pressure is arrived here. Total or exact bearing pressure, applicable bearing pressure we can say. So the same formula is applied here. So it is two way of applying the bearing pressure value instead of checking whether both are same. So it is for cross check it is made. If these both are same, then it is say true. So it is a large condition applied, what we had discussed earlier, like if the actual eccentricity in one direction is less than the limiting eccentricity, then we need to consider this row of this row, both eccentricity is limited within the limited eccentricity, then we need to consider this. And if one is exceeding, likewise we already discussed those, the same conditions are applied here with the if and formula equations, so that all cases we need to calculate likewise. So this is the bearing pressure calculation. So then it is very simple for us to add for all the load cases. So we already consider the load combinations here in the stage 2. we already calculated this. So from that we are just link all the load cases and just tap down. So here that Hy is a transverse force, shear force, and a moment we can directly link to this My load combinations which we had seen in stage 2. So Mx and vertical force also we can get from this load combinations tab. So now all this value we have calculated from the load cases from the structures, so we can copy paste the same formula. So next, coming to the vertical load, this vertical load including the weight of the foundation, weight of the subsoil along with the structure loads. So this weight, what weight we need to consider? We know that our entire foundation is subject to the submerged condition also. So depth of foundation below FGL we are considered here, but the submerged depth we discussed in the stage 2 is a 2.5 meter. That means the water table level is at 0. It means 0 from the finished ground level. It means water table is at the top of the foundation or the ground level. So here up to here the water table is there. So it means the concrete foundation is subject to loss of weight due to the water uplift forces. So it means what self weight of the concrete and the submerged soil we need to consider. There will be some variations or confusion may happen. So in that case, my suggestion is in order to calculate the bearing pressure, we need to consider the dry weight of the concrete and the soil, so that we can able to find out the effective base pressure. All other check like overturning and sliding, we need to consider the submerged weight. So that submerged weight also we already calculated here. You can see in this calculation sheet of stage 2. So it is 381 kilonewton for submerged case, but for the dry weight it is 748 or 49 kN. So not all the time that water will be stagnated in the foundation. Sometimes it will vanish due to the summer season or hot weather. So that also we need to consider. So for bearing pressure calculation, either the two way, we need to do the separate calculation for entire dry weight or and separate for submerged fully submerged condition, or else we can do it in way. So likewise, the considering the only for the bearing pressure we need to consider the dry weight of the foundation and the soil, and for the rest of the overturning and sliding we can have it as submerged weight. So now you can see here that foundation soil parameter we are considering here as a I79. I79 of this cell defined dry weight. And coming to the overturning, you can see this weight is a 446, which is derived from the I101. So you can see here this submerged weight is a I101. So this is what the weight we need to consider. For overturning and sliding alone is the submerged weight we need to consider. And for bearing pressure calculation we can consider the dry density or dry weight of the foundation and the soil, subsoil. So now hope you understand the bearing pressure calculation. So now after understanding this, all other things are very simple. So this is a cases for conductor with deviation. So we are already having in the stage 2, we arrived this both the conductor without deviation and with deviation load combinations values. So it is directly linked to that, and same way of calculation. So when coming to here, you can see that there is some reduction in other direction, that is the width direction also, due to this load case. And here it is stating it is redesign. It means this factor, this bending moment factor, sorry, bearing stress factor of safety is less than the factor which is defined here. So here for SLS load cases, the bearing resistance factor should be 1.4, but we are getting here 1.09. It means the foundation is not safe or unstable. So we need to redesign for the bearing stressor by increasing the length or width. On the other hand, there is one more recommendation or one more reference we need to consider, that is contact length reduction. So some customer technical specification used to define that this is a percentage allowed for contact length reduction. So it means that up to 80% or up to 90%, some customer used to ask to go with the reduction of contact length limitations. So the contact length should not reduce beyond 80%, means that also we need to consider. Suppose some customer used to say only at least 70% in order to do optimistic design. If they ask us to go for 70%, then this foundation will be safer. So suppose 80%, you can see that this load case is showing it is only 76% of contact length is arrived. So this percentage how we are arrived is, it is nothing but the reduction or contact length reduced due to this actual eccentricity conditions, that divided by the length. We already know the length is 5 meter and the width is 3 meter. So the same equation we are applying here, and in this direction there is no reduction of contact length. So it means the 100% of the width direction is there for contact length to the soil from the foundation. So here this direction, in these cases there is no reduction in the contact length, so we can consider 100%. So likewise so this case 2.28 is the contact length. We are having 3 meter as a width direction, so that 2.28 divided by 3 meter, only 76% we are having. So this case also stating that the foundation is not as per the recommended by the customer, which is stating 80% of the contact length. So some customer used to say 70% is sufficient, then this foundation is okay for contact length reduction. So this contact length is, there is no limitation or no regulation in as per the European standard. So this contact length reduction factor or the percentage is as per the customer recommendation. Some customer used to ask for 100%, so that is more challenge, because that foundation size will keep on increasing in order to achieve this 100%. See, for all the cases, only few cases it is okay, but even the 90% also some cases are not suitable. So let we have 80% as optimum. So now here it is a redesign. So the redesign means we need to increase the sizes. So we can increase this to 3.5 meter instead of earlier assumed 3. So now we look into that stability check. So now it is pass. Even the contact length also increased. So the 95% is the contact length here in these cases. So it is more than the 80% as per the customer recommendation. So this case also we complies. So it is now 1.48, which is greater than this 1.4. So hence safe. So this is what all about the bearing pressure calculation. So these are without deviations and with deviations. So the similar way we have calculated for ULS load case also. So here you can see this is a SLS load cases, and the ULS load cases also is the similar way we have calculated. And here the stress value or bearing pressure value is 224, which is a maximum of all this, and the factor of safety is coming 1.53, which is greater than 1.4, so hence safe. So here the load cases we are considering as ULS load cases. Here you can see these are the ULS load cases we had arrived during the stage 2. So these load cases we need to consider here. So the bearing pressure check is completed in both the SLS and ULS load cases. Now we will look into that overturning. So now the overturning is very simple. As we discussed in the first stage, if the resistant moment, overturning moment is greater than the calculated or actual bending moment with respect to the partial resistance factor, then it can be called as safe. So again this load combination we are considering from the SLS cases, longitudinal force and vertical force. Here as we said that we need to consider only the submerged load cases for overturning and sliding. So the submerged weight we are having 439.28. So this submerged weight only we need to consider for overturning and sliding. Now the moment as usual, which we calculated, which we find from the bearing pressure, and the same way we are multiplying this. So these are all same as per the bearing pressure calculation. Now the restoring moment base is nothing but the vertical P, vertical weight divided by the length in X direction. The length is 5 meter, we already assumed, and the width for Y direction divided by 2. So this is nothing but the resisting moment in X means P divided by L divided by 2. And similar like for X direction, this is P divided by B divided by 2. So this is the formula to calculate the restoring moment. This is a simple formula. So we know that the weight of the foundation along with the structure weight and the subsoil weight divided by the lever arm distance, that is effective distance, half of the distance we are multiplying for both the directions. So we are getting the restoring moment on both the direction. So now the factor of safety is very easy. So we are just dividing this restoring factor with the moment at base, that's all. So all these factors should be arrived here in both the direction, X and Y. So if it is exceeding the value of partial resistance factor as described here, then it should be unsafe. It is unsafe. But now in this case, if it is exceeding means it is safe. So here you can see that 1.6 is exceeding the 1.1, so it is safe now. So we are already having the factor, overturning factor of safety as more than the required as per the table 5, 19 and 97. So this is all about the overturning check. So here that under submerged condition only we are considering here. So then this is conductor with deviation. Earlier we calculated conductor without deviation, now it is conductor with deviation. So coming to the sliding check. So the sliding check is very simple. So here we no need to consider any moment, only the horizontal force we need to consider. So the horizontal force with the submerged condition weight we need to consider. So again here we are considering the weight as we consider in overturning check. So now the sliding resistance as we described in stage 1, how to calculate the sliding. So you can see that coefficient of sliding between soil and concrete we need to consider. So that all we calculated in stage 2 also. So here you can see that coefficient we consider is 0.38 by considering the angle of internal resistance as 30 degree. So it is 2/3 of tan 30 we are considering as 0.38. So that weight 5, that is 0.38 multiplied with the vertical load P, we are getting the sliding resistance, that is HR, in kilonewton. So now again this sliding resistance divided by actual applied horizontal forces, that is Hx in longitudinal direction and Hy in transverse direction. Both the direction we are dividing this sliding resistance with the forces, respective forces. Then we are getting the sliding factor of safety values. So here it is 4.79. So this is greater than the required factor as per the table 5 EN 1997. So then it is safe. So the same way we are applied for all the cases in conductor without deviation and conductor with deviation. So similarly we need to do for ultimate limit states also, ULS cases also. So those are here the same procedure, only the force values will change according to the load combinations. So here we need to consider this SLS cases. So here in the load combinations you can see these cases we need to consider. So now this is all about the stability check for the foundation. So these are the cases we had seen. So under the bearing pressure, the serviceability load cases, and check for overturning for serviceability load cases, check for sliding for SLS cases. And coming to the ULS also, we can check the bearing pressure, check for overturning and check for sliding. All this we are also having the subdivision as conductor with deviation, conductor without deviation. So all the load cases are checked. And here you can see that bearing pressure everything is safe, and for overturning in SLS also every cases are safe, and for sliding also all are safe, and similar like for ULS cases everything is safe, bearing pressure is safe, and overturning in ULS also safe, and sliding for ULS cases also safe. And addition to that, we also checked as per the customer recommendation the contact length 80% also we get checked. So all are greater than the 80%. So this is all about the stability check. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.